So now we reach the last part of this lecture, which is basically the learning paradigms, so the training paradigms that we can use to train our neural networks, right? So there are two approaches. So far, in all previous lectures, we only have explored the inductive setting, all right? So the inductive setting is conventional in many kind of, machine learning and deep learning models. So the key idea is that you have a training data that is independent, completely independent from the testing data. So there is an independence here. So first train, so let me write it down. So here, first, maybe I can write it this way. So first train model on train set, on the train set, and second test on the test set, okay? So these are two separate steps. These are separate steps. Now, in another example, what we could possibly do is to train and test at the same time. So for example, let's see at this, in the A figure here, we have node classification task in an inductive setting. So are giving a set of I training graphs. So we have different training graphs, and the node labels, orange and cyan colors, are known. So we have the known, of course, when we have training data, we know all the labels of the training samples, okay? So in this case, because, well, we're not doing other types of training, and if you have training data with missing or some unlabeled samples, we call that semi-supervised learning. And there is a discussion between different researchers arguing that semi-supervised is sort of transductive, but I would like to call, semi-supervised learning is when you have training. Semi-supervised learning, when training, you can have training samples can be unlabeled. So you can have some training samples with no labels, and that's still fine, but you will have your test, samples independent, okay? So so after training, basically here, you are giving a test graph, and you can assign or predict the label for each node on this test graph, for example, okay? So this is one way of doing it. Now the transductive setting is very different. In a transductive setting, we build a graph with all training and testing samples at the same time. So my adjacency matrix of the graph will have, training samples, TR, plus TS, plus testing samples. So all nodes will be combined together, okay? So it's a huge graph that is a union, that has a train, a test, but it's not just a union. These are actually connected. So it's plus, they're both connected, okay? So it's all of them together connected. So maybe I'll put N, so all of them connected, okay? So here, look, this is a testing node, and our goal is to predict on this, but to train, our network will evaluate the loss on the labeled training samples, because the training samples are labeled, so we can minimize our loss function on the training testing sample, okay? So L of W, we have here the iterations, and we optimize the loss on the training. And by optimizing the loss of on training, so remember, we have all these embeddings. So we are also updating the embeddings for the testing node. So these embeddings are being updated for the testing node and the training. So during the training, we minimize the loss over all training samples, so all training nodes. And actually what happens is that by the end of the training, we will have our embedding. So by the of the testing node. So let me use a different color here. So as we reach the end of the training, we have already predicted the labels and predicted the embedding. So we know exactly the labels of these points because we are co-learning. So basically, when you have a transductive learning paradigm, you train and test simultaneously. So you train and test jointly. So they're done together, okay? So here, in node classification in transductive setting, there is one large graph in which some of the nodes have labels. So these nodes are actually the training nodes, and the others here, these are the testing. So this is the right definition. So this should be the test data, and this should be the train data. Otherwise, we will mix it up with semi-supervised learning, all right? So we train the model to predict the known labels correctly, which are of the known labels of the training nodes, okay? And then examine the prediction on the unknown labels of the tests. So this, examining the prediction, this is to evaluate the generalizability. Evaluate the generalizability of our model. All right, so these are two different paradigms. And what we're gonna see now is like, how can we basically move from an inductive setting to a transductive one? So a transductive one to inductive is easy. You can partition the graph and you can separate them out. So I can take all the question mark nodes and put them in a single graph, right? So I do partitioning, and then I can move directly from a transductive setting to an inductive setting. And the idea is that now that we have seen all the node update rules using an inductive setting, so how can we do that for the transductive learning? So actually, it's very simple. It's not difficult. So here, first, before we move into that, let's look at the pros and the cons of inductive and transductive learning. So you can see that we have a lot of happy faces for the inductive learning. Transductive is really costly. Because you need to train on everybody, and you model the relationship. You include the testing samples when you train your model. So let's look at that. So first, we learn, so in inductive learning, so let me use this color. We learn the rule, a universal rule that maps a graph or a few of its elements, right? For example, nodes or nodes and edges, to a target output Y. And then we apply this rule to a new data. So this allows the model, like we can generalize the model and apply it to many other new data samples. In a transductive learning, it doesn't actually produce a rule, but merely a labeling of the unknown outputs, which are here. Let me write them down. These are the test nodes, right? And the second thing is that, okay, so now one drawback for the inductive learning is that we cannot access the original features of the testing samples during the training. So the testing sample may have a distribution like this. So this is the testing. And then if we have of the features, and then maybe the training is like this, right? So what happens here, we have what we call a covariate shift, a domain shift. This is a domain fracture called, okay? So it's a domain fracture between train and test data. So when you have this domain fracture, right, you have the samples are drawn from different distributions, the original distributions are different, then your inductive learning setting may fail or struggle to generalize. Like it won't give you good predictions on these samples. So think about learning like you have different samples right here. So triangles and, for example, let's say circles, but when you do the testing has a different distribution. So you have some triangles here and some circles there. So actually the real line is over here. So you have what we call a domain fracture in distribution. In this case, your black model, it will give you wrong prediction on the blue ones. So it's really not good. So what happens when you do transductive learning, the good news, and this is, I think, one of the main strengths of transductive learning, is that it considers both labeled and unlabeled data at the same time. So it has the advantage of, seeing the patterns in the testing samples, which helps make decisions. So which means we can model the relationship. We will build a graph, okay, that kind of connects all these points together. So let's put this, maybe a good graph will have something like this, okay? And then here, if sparse connections here. So what happens in this graph, that at the same time, we're able to look at the distribution of the testing of the original data, okay? Not the labels, the original features. So we want to predict the labels in, for example, or scores in regression or classification tasks. But the good news is that we don't wait until the testing stage to look at the distribution of the testing. we actually can access the distribution of all these, all these original features of all testing samples that we want to predict. So all of these will be accessible to us at the beginning, the start of the optimization. So we can know if we have a shift in the distributions, we can fix this problem better, okay? So co-learning together, you're accessing the testing data distribution during the training time, and then you're testing to do the prediction of the labels on the nodes, all right? So another thing is that for inductive learning, the good news, we don't need to store the testing nodes and their original features in memory. So the testing samples will come after the training, and it takes a split second like to kind of do the inference or the testing and getting the final predicted labels. So it's not costly. On the other hand, the transductive learning it requires a lot of high memory, like to store all the information about training and testing nodes. So it is memory costly. And then it also requires a higher computational time, because when you do message passing now, you're doing message passing between all testing nodes and training at the same time. So your graph is huge. So it's going to be really, computationally expensive, all right? Now, the last thing here, the good news about inductive learning, that you test the trained model on unseen nodes, and as you have new nodes coming in, so I want to add a new node or a new graph, I can test it immediately. So here, every time I have a new node coming in, I can test immediately, right? So we have seen that it's thanks to the weight sharing. So in inductive learning, this makes, the GNNs or GCNs generalizable to any kind of node with any neighborhood size. And this is a power of GNN that we have seen before. Now, what happens if I add a node here? So if I had a test node right here, how can I classify this node? So in a transductive setting, you need to build a relationship between this node and all other nodes and see whether they are connected or not, they are similar or not. So the problem with transductive learning, you're learning how to label this node not by applying a rule, but by kind of co-optimizing. So you need to retrain the whole model from scratch. And this is really time consuming. So not practical in real-time applications, because as you have new testing samples coming in, you need to retrain the whole model from scratch. You need to rebuild the whole graph, retrain it, because to test, you need to co-train. So you train and test jointly. So to test, you need to retrain. And that's a very big disadvantage, I would say, of transductive learning paradigms. All right, so now let's look at how we generalize, for example, inductive, how we can transform an inductive node classification to a transductive one. All right, so this is the formula that we have seen before. This is the update rule. So here, what we have for example, a new coming node. And this node, we want to basically predict we want to predict the label of this node. So it's very easy. We can feed in this node through the network. You can feed in the original embedding. You pass it forward, as I explained before. And then as you pass it forward, you will get the H, of the final layer of this node. Let's call it node test, right? And then you pass it through this kind of sigmoid function that will allow you to get the label for this node, a Y test. So it's actually not difficult. So it's very easy. And you can see here, beta is actually a scalar. So this is beta K. We have the mapping weight, and this is the transformation matrix of all nodes. So we have all nodes stacked here. So we can put all nodes, but we can also apply it to a single node, generalize this to a single node. And we have seen the formula, it's not difficult. But if you have a bunch of also testing nodes, you can stack them together. So these will be your testing nodes here. So you will have multiple testing nodes that you stack them together, and testing nodes, for example, okay? And test nodes. And this is a one vector that we added there. And yeah, so the dimensionality is consistent, and we will get basically a value right here. And this value will apply a sigmoid function to basically get the probability and the final label of this kind of testing sample or a set of testing samples if we have many testing samples in blue. All right, so these guys. Cool. Now, this is an inductive node classification. Now, if we have a transductive one, so in transductive learning, what happens is actually we will mask out. So we'll have here, we will learn these embeddings. So let's say these are two, we will mask the labels of these guys. So when we do the optimization, we will not optimize on these guys because we don't have their labels. We want to predict their labels, okay? So it's the same thing, just, when you do the transductive node classification, we need to get the labels of these two guys at the same time. So here in this formalization that we tweaked a little bit, mathematical update rule for the classification, right? So in this matrix form, we take all these nodes. So we have node 1, for example. So these are two nodes that we want to test, right? So in this case, the size of this will be, these are the test nodes, right? And then here, the size here will be the test nodes. And this is a multiplication. So what happens is that we're going to, apply this to all the test nodes. So we have the embeddings that we learned, right, of the test nodes, and we co-learned because these are updated throughout the whole graph through the message passing. So first we have the embedding, the original features of the test nodes and also the train nodes. So these are the train nodes. Let me color them for you guys. So my train nodes, we have 4 training nodes and their original embeddings, and we have 2 testing nodes and their original embeddings. And as we move them through the GNN layers, we get the updated embeddings, right? So we know how to do that in detail. And now we want to predict the label. So how to predict the label? We just pass it through the sigmoid function. So this sigmoid function. And as you guys can see, when we add this up, this will give us a horizontal row vector. And we multiply the beta k by this, one vector transpose. So we're going to get also another, the transformed vector here plus the bias. And we'll apply a sigmoid function. So this sigmoid function, the bold sigmoid function, it applies the function independently to every element of the row of the input vector. So of the row input vector. And so what we're going to get basically is an n output. So y here, y belongs to R big N, with n is number of test nodes in G in the whole graph. Okay, so if we have 2 nodes, for example, we're going to get 2 values here, final 2 values that we will apply the activation function to that for classification, and we're going to get the final labels predicted for these 2 nodes. All right, so that's how it works. It's actually very simple, so you can easily do that. So it's the same thing. So here we're optimizing over these, but in the optimization, in an inductive learning, we consider that everybody is kind of, has its label, but we do some masking in the optimization because when we have the testing nodes, we don't know these labels, so we will not use it to kind of evaluate our loss, our classification loss. If we use cross entropy will be evaluated only on the pink ground truth training nodes because we're optimizing. And then later on for evaluation, this is for, so let me write it here. So we optimize over those, over train, and we evaluate the model generalizability over test by checking the y hat here of test sample and also versus the ground truth, the y test ground truth. All right, so that's for evaluation, and this is for the training and optimization that we usually do. All right, so one question for reflection. So how to batch nodes in a transductive learning paradigm. So this shouldn't be too difficult. If you guys think about the approaches we have seen, You can also design a GCN model that does node classification. The GCN model or GNN model with different layers, it can be trained in an inductive way and transductive way, and you can compare the results of the inductive training and versus the transductive training on the same, input. You have a fixed train set, fixed test set. You can also add validation if you want. But yeah, so basically you can compare these two learning paradigms, and in terms of batching, you can try to elicit or like adopt the same batching strategy for fair comparison between these two learning paradigms. All right, sounds good. So that's all. And I think as just a recap of this lecture, you guys can try to kind of, maybe sit down after watching these videos and try to recall every single thing that we learned today. And it would be a good recall exercise, the different concepts that, you remember.